transformer changed the world, but as every engine, it has its own limits. The first and most obvious limitation of transformer-based generative models is what AI engineers call its black box nature. Generative models work. They answer questions, they generate text, and they make decisions. But there's one unsettling truth. The internal processing functions in these models are mostly unreadable to humans. This issue isn't new, it has existed since the early days of artificial neural networks. All AI engineers know that LLMs are and continue to be black boxes. You give them an input, they give you an output. What happens in between is largely invisible. There is an entire field of research dedicated to uncovering this mystery, that is mechanistic interpretability. The goal is simple in theory. Take a model apart and link its internal components, neurons, weights, activations to clear, human, understandable concepts. But in practice, it has failed. After years of work, researchers have only managed to interpret a tiny fraction of large language models, less than 1% of their internal structure. The remaining 99% unmapped, unexplained, not for a lack of effort, but because by design, they are inherently unintelligible. That's why AI researchers call it the dark matter of AI. Why this happens? In the human brain, specific neurons specialize. In generative models, they don't. Concepts aren't stored in one place, they are smeared across millions and sometimes billions of parameters and nodes. This happens because of the learning algorithm itself. At its core, it's a glorified form of curve fitting. The result? No single neuron means anything by itself. No single weight represents a clear feature. Thoughts are diffuse, memory is entangled, meaning is scattered. This leads to two serious problems. First, you can never internally trace why a model produced a specific answer. And second, auditing, debugging, and even correcting behavior becomes nearly impossible. In high-stakes systems like medicine, finance, and defense, that's not just inconvenient, it's a safety hazard. A recent MIT study revealed something even more disturbing. The researchers asked the model a simple question: where is Paris located? The model answered correctly, France. Then they asked the second question, one that makes no sense at all. Quickly sit Paris clouded? The model answered France. Why, they figured? The model just recognized a pattern, adverb followed by a verb followed by an entity, and that pattern triggered a memorized response, while ignoring the semantic incoherence of the question. Models take so many such shortcuts that hide unnoticed, and these causes all forms of adversarial vulnerabilities. Attackers can exploit it, safeguards can be bypassed, behavior can be manipulated. The second problem these models face is data inefficiency. Transformer-based models don't just need data, they devour data. Public estimates suggest that training GPT-5 required on the order of 40 trillion tokens. To put that into perspective, an average page of text contains about 500 words, which translates to around 700 tokens. That means GPT-5 consumed the equivalent of 60 billion pages, or roughly 240 million books. That's twice the number of books ever written in human history. And the catch? Much of that data isn't unique. Data samples are duplicated hundreds and even thousands of times. Why? Because transformers suffer from some disease called catastrophic forgetting. When new data is learned, it overwrites old knowledge because everything is stored in the same tangled parameters. To compensate, the same information must be shown to the model hundreds or thousands of times. This means what can be learned using 10 million data samples, current models achieve using up to 10 billion of these samples. The third problem is compute. The amount of computational requirement to train modern LLMs is staggering. Estimates for GPT-5 range from tens of millions to nearly 100 million exaflops. For context, 1 exaflop equals 1 million trillion operations per second. To put this into perspective, The most powerful supercomputer on Earth, El-Capitan, delivers about 2 exaflops. At that speed, it would need to run for months to train a single model, and that's of course assuming perfect efficiency. This level of compute intensity takes us to the next problem: energy. AI data centers now consume city-level amount of electricity. You probably heard about this in the news before, how AI strain power grids and drive up energy costs. The main culprit is GPUs, some of the most power-hungry components in modern computing. You see, training and deploying AI-generative models rely heavily on a massive network of power-hungry GPUs. This mirrors the energy dynamics of cryptocurrency mining, which also uses GPUs, and which causes intensive energy demands to the point that multiple countries had to ban crypto mining altogether. But unlike crypto mining, AI isn't optional, it's becoming foundational. And that means this isn't just a technical issue anymore, it's an economic problem, an environmental problem, and increasingly, a geopolitical one.